through this here.
Okay, so it is my great pleasure to introduce today's speaker, Victor Gurarie from University of Colorado. Victor got his PhD in 1996 from Princeton under Sasha Polyakov. He didn't continue with string theory, but he continued with many interesting papers in condensed matter physics and related topics. I remember reading Victor's very early paper on turbulence, which is very interesting, eye-opening at the time. So today, let's say Victor, after his PhD, spent some time as a postdoc at KITP in Oxford, and then he became a faculty member at University of Colorado from 2003. Today he's going to tell us about spectral form factors of attractively interacting fermions.
Thank you very much for your introduction and the offer to give this talk here. I have not been here since, I think, 2008. And I have not been to this building. I've been in a different building the last time I was here. So it's really nice to see all these new facilities that you've got and this great room even to give the talk in other areas of this building and other buildings. So today I would like to tell you about a little project that I had for the last maybe 2 or 3 years, mostly motivated by just a curiosity about how a certain things might work out. So the project I'm about to tell you, well, it's about spectral form factors, and maybe I should tell you what spectral form factors are. So spectral form factors are just these objects. It's a sum over all energy levels of some quantum system of e to the minus I, E, and T, where En are these energy levels. Well, we kind of know, we've seen these things before, but usually we don't take them very seriously in the sense, given some favorite quantum system you might have, typically you don't compute the sum. You can maybe write it down, but you're not interested in it as a function of time. And so this project attempted to take this a little bit more seriously and look at it actually as a function of time and try to understand what it's teaching us about the underlying quantum system. And now, whenever I tell people that, oh, you know, I'm interested in studying this object, everybody tells me, why are you doing it? Like, what's the good reason? And on this slide, I try to put some words, which I usually tell those people who ask me in response, why I'm doing it, why I'm really concentrating on this. But the real reason why I'm looking at this is because it's fun and because it doesn't look like it's been looked at before. It's been looked at before in some contexts, but not in the kind of context in which I'm looking at these. And also, as it turns out, as a theorist, whenever I start looking at these, I discovered that it's almost like I take old, well-known results and just turn them upside down and look at them from a different angle. And it's always nice to be able to take something which you know very well from textbooks and look at it from an angle that textbooks fail to look at. The real reason why this object is kind of fun, and as a theorist at least, is because it looks just like partition function of a system. If instead of IT, I inserted inverse temperature, it would have been partition function. And of course, partition function had been studied forever in all sorts of contexts. And I imagine you take all these partition functions and you just plug in IT in all the equations that are so familiar. And some of the equations almost don't change at all, just you put IT instead of temperature. But some of them suddenly completely change and acquire a new meaning. And just doing it was fun. But you could still say, okay, well, it's fun, but what's the, why is it useful for anything? And well, okay, so that question, to be frank, I still don't have a very good answer, but maybe a couple of answers. Whenever I bring this up, people tell me that's not good enough. It's not good enough motivation. But for me, it was good enough motivation. So first of all, something which I did not put on that slide, but this will come up later in my talk. It's been realized relatively recently that in at least some cold atom systems, and these days we put together all sorts of quantum systems using cold atoms. In some cold atom systems, you can actually measure this quantity. there's a procedure, protocol, you follow it, and out comes this as a function of time. So you can do it in the experiment, not in a solid state experiment. I don't know how I would go about measuring this in a solid state, but in cold atoms, the procedure exists. And it was even measured in some very particular, well, maybe very special cold atom systems, which made it easier to measure this kind of object, but it's been measured. So that's one thing. So it's not some abstract quantity, it's something which was measured. And second, these quantities do something as a function of time, which is reflected, or which reflects the properties, well, underlying properties of the quantum synthesis for which you're calculating this. Now, this has been known for such simple synthesis as random matrices. So if you open any textbook on random matrix theory, you'll Mechta random matrices, this will be calculated for random matrices. So at least for random matrices, this was of interest. Now, more recently, this became kind of an important object to calculate in SYK models. There are papers in high energy literature where this quantity is calculated and studied, and it turns out that its dependence on time has different scales of time, which you can study exactly how it changes as time depends on which range of time you're looking at, and you can draw various conclusions. But SYK, in some sense, it's a chaotic system, and it kind of resembles random matrix. And so I wanted to see what this quantity is for less chaotic systems. One possibility is to look at it at integrable systems. Like you can calculate it, for example, for things like transverse Ising model, which is exactly solvable, and you can just figure out what that is. But those models are very constrained, exactly solvable. We perturb away from exact solvability. It's not clear which of these features survive. And so I wanted to look at something which is neither fully chaotic and looks like random matrix theory, nor transverse field Ising model, but something in between. And somehow I ended up looking at it for attractively interacting fermions or superconductors, but I'd like to say these are not the solid state superconductors. They're more like cold atom superconductors. We have a bunch of fermions, and you turn short range attractive interactions among them. And that makes up a very nice model, which you can study, and which is also realizable in the cold atom experiment. And I'd like to understand how this behaves as a function of temperature. A function of time. And so it turns out that if you look at it as a function of time, by looking at what kind of function of time this is, you can actually deduce what kind of underlying superconductor you've got, at least so it seems. And that's what I would like to talk about today. Okay, so let's see what I've got here. So first of all, this type of object, of course, it's a trace of the evolution operator of our system. And if you look at absolute value square of this object, it's related to the correlation among energies in a quantum system. That's kind of clear. You just take absolute value square of this, Fourier transform it, and this will tell you the probability of finding two energy levels exactly the distance omega apart, where omega is the variable conjugate to time. So that would be the obvious like physical interpretation of what this says. But I'm also interested in looking at it as a function of time, not as a function of frequency. And I will concentrate on this as a function of time. So once given as this object as a function of time, you can always Fourier transform and deduce what it tells us about the energy levels of our system. Okay, so that's the first thing I wanted to say. Then I would like also to talk about some aspects of this quantity, which became prominent relatively recently. And it's an aspect that this quantity, of course, resembles partition function of a thermal system. It's almost partition function. It's just that the temperature, instead of being real, is being plugged in to be imaginary. So usually we say evolution in imaginary time gives us partition function. But here I'm taking this upside down. I'm saying calculating thermal properties of a system, but for an imaginary temperature, gives us what I'm looking at, the trace of the evolution operator. And so about 10, 15 years ago, it was brought up that maybe as a function of time, at least for some systems, trace of the evolution operator will resemble behavior of the partition function. And now partition function is often known to be singular, discontinuous, if there's underlying phase transitions. So as a function of temperature, partition function can have singular points. And so one question which was asked whether these trace of evolution operator, whether it could have singular points as a function of time now instead of temperature. And if it does, what kind of singular points those might be. And so, for example, let's take just one-dimensional classical Ising model. And the reason I'm bringing it up is because that's one object for which I can easily calculate trace of the quote-unquote evolution operator, and I can deduce how it behaves. And that's because, as everybody knows, it's very easy to calculate the partition function of the one-dimensional Ising model with, let's say, periodic boundary conditions. So you calculate it as a trace of this transfer matrix. And of course, transfer matrix has two eigenvalues, and one is cosh of J over T, and the other is sinh of J over T. And so for large n, cosh is always larger than sinh, and so the partition function is just twice cosh to the power of n. And apparently Ising was the first to actually do this calculation. And it follows from here that one-dimensional Ising model does not have phase transitions because this is an analytic function of temperature. So Z is just analytic as a function of temperature. Okay, we all know this. We studied this in school. Of course, if you repeat this calculation in 2-dimension, when it becomes much more complicated, then Z will no longer be analytic. You will uncover the phase transition that 2-dimensional Ising model has. But suppose I repeat the same thing, but for imaginary temperature. So I would calculate this as a function of time. And that's very easy. So you just take the same expression and you plug in time instead of temperature. So this IT instead of 1 over temperature. And you get trace now of this matrix. And this matrix obviously has also two eigenvalues. One of them is sine of Tj, and the other is cosine of Tj. And so the trace of the evolution operator, this spectral form factor, it's actually this expression. It's sum of cosine to the power of n plus sine to the power of n. But unlike the partition function as a function of temperature, here, sometimes cosine is larger than sine, and sometimes the sine is larger than cosine. So here we could have said, we just say that hyperbolic sine is much less, well, it's less than cosine, and nth power enhances that difference, so only cosine survives. But this guy is either cosine or sine, depending on the values of Tj. And actually, I plotted it here, and to make it more visible, I plotted logarithm of z, which is kind of like partition function of this z. So in other words, logarithm of the spectral form factor divided by n. And so it's discontinuous because sometimes it's a logarithm of sine and sometimes it's logarithm of cosine. And in between there are points where logarithm of z squared has discontinuity in the derivative. So it's log z squared is continuous, but as sine gets replaced by cosine back, we see the discontinuity in the derivative. And by analogy with what happens here, whenever we see partition function and free energy, which are continuous, but the derivative with respect to temperature is discontinuous, let's say this is first order phase transitions. But here I replace temperature by time, and I say, oh, these are first order phase transitions in the one-dimensional Ising model. Well, okay, it's of course all great to know, but then a question comes up, what does it signify? And are these really phase transitions? And so a number of authors, including this guy, they spend a lot of time trying to tie these to some sort of underlying quantum phase transitions with variable degree of success. For example, what these authors would do is that they would promote one-dimensional Ising model to one part of a transverse field quantum Ising model. And would argue that the discontinuities are a reflection of quantum phase transitions which occur in one-dimensional quantum transverse field Ising model. And of course, you can think of this transverse field Ising model has sums over products of sigma z's and it has sigma x's, as everybody knows. And if you get rid of sigma x's, it just becomes one-dimensional Ising model. So somehow what I'm telling you is that going back to quantum transverse field Ising model teaches you something. But I would say, despite a large number of literature on the subject, the jury is still out whether this has anything to do with quantum phase transitions or dynamic, what they would call it dynamic quantum phase transitions because they occur in time. It doesn't seem like there's any quantum transitions here. And so I don't want to focus too much on this terminology, but I am interested in singularities in this quantity Z in general. And as you can see, they're kind of ubiquitous, even one-dimensional Ising model has them. And I would like to understand under what conditions these singularities may occur. And that's kind of the theme of what I will talk about today. The singularities in z squared, z is defined in this way, and what do they signify? And so because I'm talking about singularities, I thought I would mention once a little bit more about what's known about them in the context of statistical mechanics models, such as one-dimensional transverse fieldizing. So it turns out that those were studied first by Michael Fisher in 1960s, and you can find out the original papers where they, but of course, always in the context of some classical statistical mechanic model, not fully quantum interacting many-body system. And so Michael Fisher and others who came later argued that given this quantity, which is kind of like, well, for them it was a partition function which was analytically continued to complex temperatures. But for us, it might be trace of evolution operator analytically continuous to complex times, whichever way you prefer. But it's this object where W is arbitrary complex number. And so if W is real, we're looking at these spectral form factors. If W is imaginary, we're looking at thermal partition function. But W can also be in between. And so in general, we can argue that these objects can be decomposed in terms of product of zeros, points in a complex plane where it vanishes, and those are Fisher zeros. So Z of W will vanish at certain WJs. And then zeros in a thermodynamic limit may accumulate in various areas. And these authors famously argued that in general, these are domains on the complex plane, not just lines. Somehow, I think in the one-dimensionalizing model, which I showed to you in the previous slide, these are lines, and that is easy. You just analyze where those Z's vanish, and you see that they vanish along lines. But more generally, they vanish in areas. But somehow it doesn't matter to the end conclusion. The conclusion is, given those zeros, and if they accumulate in some region, derivative of the logarithm of this with respect to time looks like this sum. And this sum could be discontinuous as a function of W, or can have other singularities depending on where exactly those zeros are located. So log of that translates into, and you differentiate it, translates as 1 over this. And you know that if WJs are densely filling some region, then within that region, you can have singularity. If it's a line, for example, this will be discontinuous as W crosses this line. And so that's how zeros are related to singularities. You always look for zeros to identify singularities. And if you found zeros, if it's just one zero, it's not going to do anything. But if there are many zeros, they'll somehow talk to each other and produce singularity. Okay, so that's was discussed back in 1970s and 80s in the context of statistical mechanics. So one more preliminary slide, which I wanted to show, was that there is a related quantity, which Marcus Heil and others spend a lot of time studying, which is worth looking at, but it's a little bit more complex than what I would like to look at. So instead of looking at just trace of the evolution operators, those authors would look at a different situation when you have a system which is governed by a Hamiltonian, controlled by some parameter G. Maybe it's interaction strength, some other typical parameter. And the Hamiltonian has a ground state, let's say. And suppose you do a quantum quench. You change this parameter from G naught to some G final. I don't hit G final, but actually everywhere else I wrote just G. So from G naught to G, you switch the G from G naught to G. And then evolve initial ground state, which is no longer the ground state once G is switched from G naught to this G. So psi naught is no longer ground state of this. You evolve it with a new Hamiltonian H of G, and then project back into the initial state. And that is called Loschmidt amplitude. And there is a reason for that, because it's related to Loschmidt, what used to be called Loschmidt echo, although the connection is not 100% straightforward. It's less. It's related and it's very similar, but not quite what in the past was called Loschmidt echo. But these days, people just call this quantity Loschmidt echo, absolute value square of this. And so if you look at this quantity, it can be decomposed. If you take, well, you know, you can diagonalize H in terms of some eigenstates and eigenstates of this H. Of course, you can insert the complete set of states between here, and then a Loschmidt amplitude can be decomposed in terms of eigenstates of H in this way. And if you stare at it, oh, and of course, I should have written sum, right? There's a sum over n in front here, which I somehow missed when I was putting in this equation. So it looks just like that spectral form factor, but there is this prefactor at psi naught.
And the eigenvalue h at g.
Yes, and eigenvalue is h of g. Since and psi naught is ground state of h of g naught, which and it's not an eigenstate of h of g. Otherwise, it would have been too simple here. And there is a sum over n here. So you can see that if psi naught somehow has equal overlap with every eigenstate of h of g, then this reduces to spectral form factor. If all of these quantities are n independent, but in practice, they will be n dependent. And so you can make your problem a little bit more complicated and study this quantity, g of t as a function of time, as opposed to just spectral form factor, which does not include this weight in front. And so there was a hope again that looking at this, you can maybe learn something about the initial state and the final Hamiltonian. There was even a conjecture that given some initial state which lies in a particular phase of a quantum system, and given h of g, which is a Hamiltonian describing a different phase of the quantum system, then this Loschmidt amplitude will have periodic singularities occurring at times, which somehow signify that you had the audacity to quench from one phase to another phase. Somehow g naught and final g are lying in two different phases. And now it turns out that's exactly how it works for transverse field Ising model, which got everybody excited. So if you calculate this for transverse field Ising, and if you put psi naught in one phase, and h of g will describe a different phase, these will have periodic singularities. But subsequently, it was found that there are some models which violate this, and as far as I understand, no general principle which relates singularities and these to underlying quantum phase transitions were identified, or if there were, counterexamples were found. So I'm not sure if this is the program I would like to pursue, but I kind of want to have it in mind that there are these quantities and they may have singularities, and in part is because they were explored by many people. But here I would like to point out that so the original transverse field Ising model paper it's from 11 years ago, which pointed out that singularities in transverse field Ising model signify quench across quantum phase transition. So that's this one. And then it was actually generalized in a way which is relevant to what I'm about to do. This was studied for non-interacting fermions. So you had a Hamiltonian of non-interacting fermions, which was quenched across a topological phase transition. So non-interacting Hamiltonians for fermions can belong to one of the classes of topological insulators. So they would look at one topological insulator and they would say, what if I take a ground state of H for this Hamiltonian, and I change its parameter. Let's say ground state is non-topological, but I change the Hamiltonian, so now it's topological. And in this case, for non-interacting fermions in this work, actually there was some connection between quenching across phase transitions and topological phase transitions and singularities and Loschmidt echo were found. Subsequently, some counterexamples of that were also found. But the most interesting to me also is that this phenomenon was actually observed. In particular, these guys here, this is an experimental group in Innsbruck who worked with ions, and they were able to recreate this transverse field Ising model, although with long-range interactions. And they were literally measured that Loschmidt echo by evolving wave function and projecting it back and measuring what that was and seeing these singularities. And you may again say, why did they do it? Maybe because they could, because they had a system and which they could measure, and they wanted to find something to measure, and somebody told them, why wouldn't you measure this? And they said, okay, let's measure it. And they saw that that quantity was singular. They measured specifically Loschmidt echo for the transverse field Ising model in this work. Okay, and there was another experimental paper, which is also relevant. But now my own history of working with this was that, well, I was sort of plugged into this community somewhat, and I studied Loschmidt echo for some quantum, many body localized systems, which is a whole other direction of where we could go. But later I looked at Loschmidt echo in superconductors, and I found some interesting features of Loschmidt echo which inspired me then to say, you know, maybe Loschmidt echo is very complicated to have some initial state, propagation with some other Hamiltonian. Why wouldn't I just look at spectral form factors? And I found very similar features in spectral form factors of superconductors themselves. And that's what I would like to concentrate on. It's simpler and sort of more transparent than Loschmidt echo. And it only has as much information as Loschmidt echo, although some people would say Loschmidt echo contains information about quench as well. Spectral form factor doesn't, but it's up to your interpretation. But so now I think is a good time for me to tell you about a couple of models which I was able to solve. Some of them I solved, some I didn't solve, but I gave arguments that the features which well, there are certain features which we should be able to see in the spectral form factors. And so a simple model for which which is sort of like an inspiration for more complex models of interacting fermions that I would like to look at and calculate spectral form factor. It's a model of, we like to call them flat band interacting fermions. So it's a number of fermions, spin up and spin down, which occupy capital N energy levels, which are all degenerate. They all have energy epsilon. And so in that way, they differ from what we're usually used to as fermions. Usually fermions have some dispersion, states labeled by momenta with energy, which is a function of this momentum. But here, all energies are the same. That simplifies significantly this compared to conventional superconductors when you have fermions which are flying around, which are interacting attractively. But so these guys, they don't fly. They just sit on this energy level epsilon, but there are n, capital N of these, and actually 2n. Spin up and spin down, both can occupy this energy level. And they're all interacting attractively in a kind of all-to-all sense. Every fermion interacts, well, every pair, I should say, every pair of fermions interact with a pair of fermions. So that was my Hamiltonian. And the reason I'm going to look at it is because for this Hamiltonian, I can calculate spectral form factor exactly. And I use it as an inspiration then to look at more complex real interacting fermions, which correspond to superconductors, for which I will not be able to calculate spectral form factor exactly, but I will be able to point out its main features, working first from my understanding of this. Once when I think I gave this talk before only once, and I actually reversed the order, which I talked about, because I first talked about superconductors and then about this model. And I found that talking immediately about superconductors introduces so many features, which all come at once. And it's kind of too much information. Well, this model is so simple that you can sort of visualize it. And it's easy at first to talk about this model, although maybe it's not as interesting as full superconductors where fermions have dispersion. But okay, so one observation actually is that this model, as abstract as it looks, it also maps into a model of interaction spins. That's because pairs of fermions, so creating or annihilating two fermions together, spin up and spin down, like here. I create spin up and I create spin down. This can be equivalent or can be modeled by flipping a spin 1/2. Actually, this type of spins, so creating a pair or destroying a pair being spin up or spin down operation, this was first pointed out by Anderson in presumably late 1950s, early 1960s. In his object, pair creation operator and pair annihilation operator. So these are called operators of raising and lowering operators of Anderson pseudospin. So these objects are Anderson pseudospins. So you see I replace creating two fermions labeled by n by a single spin 1/2 also labeled by n. And this is annihilation of spin 1/2 and k. There's always typos, no matter how much you look at this. Of course, this is Sn, Sm, summation over Nm. And I'll fix this as soon as the talk is over. So I don't have a slide with something wrong. But yes, this is Sn and this is Sm. Because this is a creation of spin n, and well, we'll flip up spin n. And this is the, if you flip down the spin m, and this then becomes an interaction operator between spin n and spin m. And this, of course, is just SZ, because you create two fermions with spin up and spin down together, and that costs energy epsilon per fermion, which is 2 epsilon altogether. And so if this SZ is spin 1/2, so flipping that spin costs energy epsilon. And I put 2 in front to represent that it two fermions together. Okay, and so in this way, actually, this Hamiltonian has been routinely created in something called cavity QED experiments, where instead of fermions, they're talking about two-level systems, typically states inside some atoms, which interact with the electromagnetic field with a cavity mode. And depending on exactly how they interact with cavity mode, you could imagine them interacting in a way which produces this Hamiltonian. So I'm not gonna say more about this. But this was created experimentally and actually studied in many different contexts. So maybe not in this language, but definitely in the language of spins. Now, if I'm a theorist and I would like to study this Hamiltonian, or maybe this one, I will do it in the way how we study superconductors. I just say, I replace pairs of fermions here by something which I can call a gap function. That's what we do for superconductors. So AA is gap delta, and A dagger is gap delta bar. And the Hamiltonian becomes quadratic, except it also has this delta, which initially I don't know what it is. But it is quadratic though, so it's solvable as long as I know delta. And then we know what we have to do at that point on. We write down gap equation, which says that delta is given by expectation of two annihilation operators. So delta essentially replaces this object here. It replaces it by taking this object, calculating its expectation, and then calling the result delta.
Victor, is this formula with spins? I guess it's a small misprint. In the last term, it's n comma n and n.
This is supposed to be m. So it's s plus n, s minus m.
Right. And that means that the sum is decomposed to.
Yes, it's really.
It's written kind of. It's such that this obvious fact is hidden, right?
Yeah, I agree. It is absolute
It's a
value
sum of-
square.
It's a square of
Sn plus, right? It is a product of two terms. It's an all-to-all interaction, and that's why actually, in some sense, introducing gap function is exact here because it's like all-to-all model. Everybody talks to everybody else, and so unlike superconductors, where we can argue whether you can apply this or not, here this just kind of like works exactly or almost exactly. And so working out this expectation, we get this gap equation, which I hope everybody is familiar with. That's what we get in superconductivity. This is a standard gap equation in superconductivity. The difference that the usual in superconductivity, this also involves summation over all momenta over all energies of fermions, which form the superconductor. But here, all fermions have a single energy epsilon, so there's no summation. It's just this ratio gives you 1 over g. And it's kind of fun to work out solution to that equation. It turns out that unlike for superconductors, for which this equation has always a solution with non-zero delta. That's why attractively interacting fermions, no matter how weakly they interact, they always form a superconductor. But for these guys, it's not exactly true. So depending on values of these parameters epsilon and g, sometimes you do not have solutions with non-zero delta, and sometimes you do. And this is a phase diagram, which actually I was staring at this equation and just plotted this diagram, and I hope I plotted it correctly. So for small enough epsilon, delta is non-zero, just comes out of solveness. But if epsilon is large enough, delta becomes 0. So everywhere below this dashed line, delta is non-zero. Same with temperature, although as you change temperature, this is less strange because superconductivity goes away as you crank up temperature, and it clearly goes away here. But it also goes away when you change epsilon, which typically is not what happens to superconductors. But this is not a superconductor. So this model in this form, in the applications to cavity QED, does have a transition, which somehow is called super radiant transition. Because delta somehow is the density of photons which interact with your two-level systems. And so here you have a lot of photons inside your cavity, and outside you don't have photons. That's why it's called super radiant transition. And so this transition is known very well, and you need to have all fermions having the same energy, or all spins having the same energy to have it. The moment you say fermions have energies which vary with them, somehow this transition along the horizontal line goes away. Okay, good. So that we understand this model, but that's not what I want to do with it. This is something which was known for 50 years, 70 years, for a very long time. But I would like to calculate not the partition function, but I'd like to calculate trace of evolution operator. And now it takes maybe a little bit of an effort to understand how you would calculate trace of evolution operator for this model. But the main thing which will happen if you attempt to do this is wherever you write down a formula at some temperature T, and you would like to reinterpret it as giving you spectral form factor, you need to replace temperature by time multiplied by I, well, inverse time multiplied by I. And so in particular, if you have this gap equation, you see temperature here, you should immediately replace it by I multiplied by time inverse, which suddenly converts hyperbolic tangent to real tangent and put an I in front. Now, again, by talking to people not deeply interested in this problem, but just listening to how I propose to address it, many people will get really upset and they would say, what are you doing here? What is this I? I don't understand. This is an equation. I never saw it before. Something must be wrong with this equation. Or maybe I should even say, not only talking to people, but exchanging opinions with referees who refer my papers with an equation like this. I only wrote maybe 2 papers on the subject, but both times there was a lot of back and forth. This equation looks unpleasant, but you can derive it. You can start with that Hamiltonian I had on the previous slide and say, I'm interested in studying trace of evolution operator. What is delta? And well, delta will be this object. And actually it's given here. So thermal delta is given by this when I average over Gibbs distribution. But the delta in the context that I'm interested in is given by this with minus E energy levels time instead of energy divided by temperature. And so I need to solve this equation then. But this equation has a strange feature. And again, that's the feature which nobody likes somehow when they look at it for the first time. This equation cannot have solutions where delta bar, delta is a real number. So we're used to delta bar being complex conjugate of delta. So delta bar delta should be real. But here, any solution delta bar delta has to be not real, because if it is real, then this is real and this is real, but there's an I in front. There's no way left-hand side can be equal to the right-hand side, unless there is some singular, like, delta bar goes to infinity or something. Well, I'm saying that even that I'm not sure you can do. You somehow have to get rid of this I altogether. On the right-hand side, everything is real. So all solutions are complex or zero. Maybe they're zero. And so then at that point, the question comes up, what does it mean that delta bar is zero? And I mean, delta bar is complex. And one of the big reasons I'm looking at this flat band model is because I can solve it exactly, even without introducing delta. And then I can just ask, is delta complex or not? Again, often I'm asked, so the complex delta bar being complex, how is it compatible with equations of motion? Well, at least at the first glance, it is not incompatible. Delta is given by this expression, where there is an I here. So delta bar is given by that same expression with creation operators here instead of annihilation, but this is still minus. So the equation for delta bar will not be complex conjugate of the equation for delta. And so finding delta bar being complex conjugate of delta doesn't sound natural, even though we're not used to it. Okay, good. So yes.
Is that gap equation some saddle point?
Definitely, it is a saddle. You can derive it as a saddle point of the corresponding functional integral. And, so what's interesting, I'm not going to show it on slides because it's too technical, but it's enough to look at functional integral. It's enough to look at Feynman functional integral. You don't need to look at Keldysh functional integral or anything more fancier than this, even though this kind of looks like time evolution. You think maybe I need to use Keldysh technique, but you don't, because you only evolve a state and then project it back into the initial state and do a trace. So you do Feynman integral, which is what you do when you compute thermal objects, when you compute thermal partition function, or you do it in imaginary time. You just repeat the same thing, but in real time, and then derive all these equations. Okay, now quickly, given this model, but again, I did the same typo here because I think I copied pasted that equation. This is SM, not SN. You can actually solve it, at least find its energy levels, because you can just add up all the spins into one big spin. So it's just like, it's a Hamiltonian for a single spin on some level. And then you can just diagonalize this Hamiltonian. And of course, you introduce a quantum number, which is total spin, which I called K here. And then you introduce projection of that spin onto the z-axis, which you call M. And so this becomes 2 epsilon M, and you can convince yourself that this is this expression written here. And the only question which remains is what's the degeneracy of every energy level? And it's a little complicated because the spin is made of large number of spin 1/2s. So you have to figure out what that degeneracy is. But as always, it turns out that it's enough to open Landau-Lifshitz on certain page. And this equation is given in Landau-Lifshitz, so you can read it off. You don't have to remember how it goes. And then exact spectral form factor becomes just this expression, sum over all these energy levels, labeled by projection of the spin and total spin, which total spin takes any values between 0 and half of capital N. And you just have to do this sum. And now, of course, this sum, you cannot do it analytically as far as I know. It's a complicated sum, but you can do it numerically and you can plot spectral form factor. And that's what I try to do. So I'm going to show it on the next slide. So I know it could be a little bit confusing, but so what's shown in blue is numerical evaluation of that sum. This is time. This is absolute value, with logarithm of absolute value of z divided by n. So what I see is that the dots, and I mean, there is some, it's not easy to evaluate the sum because n is fairly large. We took n to be several hundred. It takes some effort. You have to coax Mathematica into computing this correctly, but you can do it with Mathematica. And so you see these big bumps and then some sort of a line which almost looks like there's some kind of underlying smooth line going through, but it gets separate. So every now and then it gets replaced by these bumps. And there's a line and a bump, a line and a bump, and so on. And I'll tell you what red dots are in a second, but for now, just blue. Blue means is evaluating this. Bump, line, bump, line, bump, line. Now, if you look at this a little bit more carefully and you reanalyze this using the gap equation, which I showed to you earlier, you can convince yourself that actually these bumps are nothing but the saddle points or solutions of gap equation corresponding to delta equal to 0. I mean, you can imagine the solution of saddle point equation or gap equation where delta is 0. Now, if delta is 0, this entire Hamiltonian just becomes free fermions, or a single spin with Zeeman energy 2 epsilon. Well, not single, but n, capital N of these spins, 1 per each pair of fermions. And so it's very easy to calculate anything you would like, it's just fermions. So the object Z is just a sum, e to the I epsilon C plus e to the minus I epsilon C. It's two-level system raised to the nth power. So it's an n to the nth power, but then I cancel out n by dividing by this n. And so it's logarithm of cosine epsilon t. And if you plot logarithm of cosine epsilon t, that's what you will get. So I kind of just, I didn't really plot them on top of this, but I schematically showed. So these bumps, if I continue them with yellow lines together, these are logarithms of cosine t. And that's what I wrote here, log of 2 cosine epsilon t. That's literally these things, 1, 2, 3, 4. So, and it just, not all of this is reflected in the blue curve, but clearly these bumps are the times t for which the solution to the gap equation corresponds to delta equal to 0. Okay, so for some times, solution is delta equal to 0. But what are these lines? And so with working with that gap equation a little bit longer, you can see that these lines which connect these bumps in some way, these are solutions of the gap equations corresponding to complex delta bar. You can find them. You can't quite find them analytically because it's a transcendental equation. So there's some tangent there and algebraic functions, but you can solve it numerically. You can also qualitatively find where these solutions lie. And among these solutions, there is the one which gives the largest contribution to Z. And if you plot it, it'll be these lines. And the red dots actually represent calculating that solution at various times, including even when that solution is not the right one, when it's in between or underneath this hump. So pretty much what's happening, there are two solutions here. One is complex delta bar. The other is delta equal to 0, and they compete with each other. Whichever one is larger gives you the answer. And so there are intervals of time between here and here, for example, when this is the answer because it's larger. Then there are other intervals in time when log twice cosine are these yellow lines, and they're below the actual answer. And the actual answer is given by contribution of the complex delta bar. Okay, and so the only reason I went through all of this is to kind of convince everybody that there is complex delta bar. It's not my imagination. It's not, it didn't come from some random equation which I pulled out of here. I mean, when you plot the solution to this problem without any gap function, the only way for that to be described by gap functions is if you say that delta delta bar is complex. Okay, good. So yes, complex delta delta bar are these stretches in between these humps. All right, so I have a slide here which I don't want to focus on. Once you have delta delta bar complex, you start worrying what does it mean as far as energies. Excitations energies are complex. Don't have to worry about this. I actually don't have a good answer for that other than to say that complex excitation energies correspond to unstable quantum particles. And I have some argument here, which I put here in case if I have a lot of time. It doesn't look like I have a lot of time, so I don't think I need to focus on what's written here. These are redefining conventional Green's functions, but in the presence of, well, of time instead of temperature. So look at a thermal Green's function, but I'm looking at them as a function of, well, as with temperature being replaced by time.
Just
And
a question.
try to argue.
A question here, is this excitation energy also time dependent?
So it depends on t. So time t is not really evolution time. My evolution time goes between 0 and t. Time t is the time over which I'm computing spectral form factor. In other words, I take my wave function, evolve it over time t, and then calculate spectral form factor over this time. So I don't like thinking of it as some kind of time over which I'm evolving. This time fixes more like boundary conditions, like temperature does in formalism, thermal formalism. So from that point of view, E is a function of T, but T is boundary conditions and not time over which I'm evolving. Yes.
In the comparison of your thermal gap equation to the IT gap equation, you could also maybe interpret imaginary unit as going with the interaction strength, so that you have a complex coupling instead of a complex delta delta bar. Did you ever
Yes.
think about this? And has this like any relation to, I don't know, PT symmetry or something like that?
Okay. Yeah. So I have not looked at it in part because I wouldn't know how to measure it. Well, spectral form factor, I do know how to measure it since people already measured something related, and there are suggestions for this. So I'm a pretty abstract kind of person, but maybe I'm not that abstract. I don't know what happens if I make Hamiltonian explicitly non-Hermitian. I know there is this PT symmetric quantum mechanics, which some people study. Furthermore, I was here on Friday, but on that same Friday, Carl Bender gave a talk on this subject in Boulder, which I missed because I was here. So I don't know what he said, but I'm not sure simply what that would mean to make G complex. While making temperature imaginary just means I'm studying things in time, and I think I understand what this means. It's okay. The simple answer is that I don't know what it would correspond to make G imaginary. But okay, so I do want to finish in 10 minutes, and I think I went intentionally slowly because I gave this talk fast once, and I don't think that had a desired effect, so I was trying to go slow. All right, but so finally we can now come to the main subject of this talk, which is let's look at real interacting fermions, not some abstract two-level systems. So imagine that I have some fermions with some dispersion, epsilon of p, a bunch of spinful fermions, they interact. Now the conventional approach to this is to remove p not equal to 0, because somehow in the mean field, and I would like to look at the mean field with gap function, I only want to leave Cooper pairs here. So Cooper pair being created, Cooper pair being annihilated, and then I can describe it again using gap function. So that's conventional, how we approach superconductivity. And so, okay, I have that. And now, let's say, so suppose I'm given this, go back one second. Suppose I'm given this gap function, then I can diagonalize this Hamiltonian and I can calculate everything, including this spectral form factor. And if I do, well, I mean, the Hamiltonian breaks into, it's really, again, sum over P. So this is Hamiltonian per momentum. And within each sector, this can be diagonalized. These are my Bogoliubov quasi-particles with the spectrum. And now the spectral form factor becomes product of cosines of these energies times time. So that's what the reason I went through this is because I wanted to look at this formula. So this is true for any gap function. Given a gap function, this is 2x2 system, 2x2 Hamiltonian energy levels. This is the Z. That's what it is. And again, I guess I say that thermal partition function looks like cautious, and that everybody must have seen at some point. But this is a version of that, but calculating in time. Okay, but so now this is all good, but I need to know what delta is. And just like for my problem, which I dealt with before, I need to make temperature imaginary. So now I get the real gap equation, which people solve in superconductivity, but with an ion tangent instead of hyperbolic tangent. And this is a very complicated equation. I don't know how to solve it, but I do know that if it has solutions, delta delta bar, well, non-trivial solutions, delta delta bar has to be complex. And I've seen it in a model with flat band fermions. So then E of P is also going to be complex. E of P is the square root of epsilon plus delta delta bar. So this is E of P here. That's defined in this. So this E of P has to be complex. Okay, so that's Z is just a product of some cosines, which are some functions of T, where E of P is some complex functions of P. E of P can also be functions of T itself, because delta can be a function of T via the solution of this equation, which has T in it and delta. So delta will be a function of T if you solve it. Okay, but so from here, it doesn't really, I don't really know what Z does. And I actually don't know fully, but my guess is that it does something similar to what Z does for that model of fermions, flat band fermions, which I looked at before, which is Z will probably have discontinuities in derivatives having to do with either one solution of this equation contributing or another. And so as we switch from one solution to another, Z will be continuous, but its derivatives will be discontinuous. So first order quote unquote phase transition in the terminology introduced by Marcus Heil and others in the past. But let's see. I would like to look now at a different superconductor, P plus IP superconductor, which was my favorite because I spent 20 years studying it in the context of cold atoms. And so P plus IP superconductor happens when you have identical fermions, which don't have spin, and they have to interact via P wave interactions. And in particular, there should be powers of momenta sitting here. Otherwise, this would be zero, because as you sum over Q and K goes to minus K. This, if there was no coefficient in front, this is antisymmetric and the K goes to minus K. But this coefficient in front symmetrizes, well, makes it symmetric again together. And that's a famous expression for P wave interactions among identical fermions, which cannot interact via S wave interactions. And now let me try to do the same thing that I've done for my fermions before, but now for these P wave superconductors. And this is where I'll start getting something interesting. So again, my Hamiltonian's again a sum of these terms. That's per momentum. So if I write this in this number basis, so to say, and from looking at it again, the spectral form factor is just a product of cosines, EP of T. But EP now are eigenvalues of this, which is square root of epsilon squared plus delta delta bar P squared. And I wrote here P squared in red because I wanted to emphasize that there's P squared here, which was not there in all the examples I looked at before, but now we have P squared. And this P squared does something interesting, namely, if P is zero, this is real. If P is non-zero, this is complex, because delta delta bar should be complex. Unless delta delta bar is zero, maybe for some times, so delta delta bar is zero. But if it's non-zero, it's complex, and then this is complex, but only for non-zero P. For zero P, it's real. And that allows me to make to come very quickly to the following conclusion, which is pretty much the punchline of what I wanted to say. So there's a special P equal to zero, for which E of P is real. And then this cosine, depending on time, T, which is the time at which I'm measuring the Z, calculating the Z, the cosine will vanish periodically. It is that zero, Fisher zero, which we were discussing earlier. And we know that whenever there is Fisher zero, there could be something interesting going on around it. And so it's easy to convince yourself, so those zeros will occur periodically in time, at these times, when the cosine of, if delta delta bar is equal to zero, if P squared is equal to zero, then EP is just epsilon. If EP is equal to epsilon at P equal to zero, then at these times, cosine vanishes. But now the big question is what happens in the vicinity of that cosine and vanishing. And so you can write down an expansion of cosine for slightly non-zero p and for t slightly deviating from these times, and you can convince yourself that this cosine goes as t minus Tn. Well, it should vanish when t is equal to Tn, and it should also vanish when p goes to 0. So there is alpha p squared. Well, alpha is some complex number. It has to do with delta bar, how complex it is. And then, given this form of the cosine, you plug it in here, and you do derivative of the logarithm, and you see the derivative of this logarithm goes logarithmically just by staring at this integral. And it's exactly that phenomenon that I've discussed before. And so suddenly log z developed a singularity, which actually goes as, well, z is continuous, but its derivative blows up as log of t minus Tn. And that's different from derivative having discontinuous derivatives. So a simpler mechanism, discontinuous derivatives in log z. This is a more subtle thing, logarithmic derivative of log z. Okay, so somehow, as you see, this feature is reflecting the fact that the gap function vanishes when p goes to 0. There's a special point p equal to 0 where there's no gap. And so it turns out that similar stuff occurs also in other superconductors. You can think about it a little bit, and you can convince yourself that certain conditions for this type of unknown analyticities. So first of all, you would like delta of p to vanish for some p. You want to have excitation spectrum which is gapful, and almost always the topological superconductor, such as this P-wave superconductor, although it could be trivial phase of a topological superconductor. Depending on what you're dealing with, well, anyway, so these conditions are sufficient to generate this type of logarithmic singularities. And actually, maybe the last thing which I wanted to show is that we went through various examples. I mean, you need to be inspired by some examples of superconductors, and you can come up with all sorts of superconductors, but an easy examples are the ones from the periodic table of topological superconductors. And we went through all of them, and we discovered that they all have singularities in log z, but singularity depends on the dimensionality of space. All the two-dimensional superconductors, various classes, have log singularity, and three-dimensionals have square root singularity. So that's the singularity in the derivative of log z. So derivative of log z actually is continuous, but the second derivative blows up if you're in 3 dimensions. And so we think that this is sort of kind of something interesting. So it's some sort of a reflection of the structure of the order parameter of superconductor in the spectral form factor, which only appears if the superconductor has these features. So featureless superconductor with gap function which doesn't vary, doesn't have these singularities. Now, I know that it's pretty much end of my hour, and this is the time when I would like to finish. I did prepare more slides in case if I decide to speak faster. But let me see. Let me see. I'd like to finish somewhere. Yes, why wouldn't I finish here? So I'm going to skip those slides and just to show one of my last slides, this one, for example. So that summarizes what I told you in this hour. So spectral form factor is non-analytic for topologicals and also some others, unconventional superconductors. We debated a lot how to call them. So these are superconductors where the gap function vanishes at some momenta, and they may or may not be topological, but that's the kind of the requirement we have. And even the fact that gapful or gapless is also, some gapless superconductors have this feature, although also have similar singularities in the spectral form factor. But okay, not, well, anyway, there's more you need to know about them to conclude that they have this singularity as well. For topological superconductors, it's very robust. You have this, you must have singularities in spectral form factors. Now, they can be potentially measured. So I never actually talked about it, and I don't think I should be talking about it because my hour is up, but there is a way, there's a protocol suggested to measure spectral form factors. I mean, Loschmidt echo is kind of easy. Loschmidt echo, you prepare a state, you evolve it, and you calculate or measure probability that you end up with the same state you started with. Spectral form factor is a little bit more complicated because you need to sum these amplitudes. And at best you can measure probabilities, not amplitudes. But there is a specific proposal due to Peter's group, how to measure them. at least in a system of ions. Maybe in other systems would be harder, but in ions, it's just something experimentalists can do and just tell you what it is. And this type of system can be modeled with ions, which is a whole other thing which I could talk about, but I will not. And so they can be used as a test for the structure of the gap function. And I would also say that this whole work, one of the reasons I did it is because I felt like I've taken something well-known, thermalism of thermal Green's functions, thermal partition functions, and thermal path integrals, and I put it upside down by making temperature imaginary, and suddenly I found new features which were not available in a formalism of thermal partition functions, because I get all these extra eyes in strategic places, which telling me something that I'm computing spectral form factor and not partition functions. And so that was one of the reasons, or one of my motivations in the first place. I just wanted to see how equations which we know and love manifest themselves in this new setting. But as I said, it still perhaps is interesting just as a new way of looking at certain quantum systems, in this case, interacting fermions. So since my time is up, I should just stop here. Thank you.
So I guess you emphasize this for this logarithmic non-analyticity in your Loschmidt amplitude. The p equal to 0 is very important.
Yes,
In that gap
for
function.
these superconductors, which I looked at the very end.
Right. So that would that mean just it's deep inside of the Fermi sea, very far away.
Yes.
That's usually.
So on the one hand, it's deep inside. Well, yes, but notice we are not looking at low energy equilibrium properties. We're somehow reflecting the property of the entire spectrum, since we're looking at spectral form factor. And so we're probing everything. So we're not just probing the vicinity of, let's say, lowest line excitation. Well, there's a gapful system, so there's no Fermi surface, but we're definitely not probing the low line excitations of the system. We probe the entire available spectrum. And it's crucial for this construction that the gap function must vanish at p equal to 0. And that by itself is very robust. So you cannot, gap function cannot not to vanish at p equal to 0. Well, in this case, it comes from
But usually,
the fermionic nature of particles.
sometimes deep inside Fermi sea, maybe the gap function amplitude, like delta is small.
Well, so here is enforced by Pauli principle. So you cannot have delta at p equal to 0, which is non-zero. And I think pretty much in all other examples, when gap function, okay, now I'll take my words back. You can come up with examples which are a little bit more sophisticated. So one of my favorite examples here is that, so it's known very well that there are some S-wave superconductors in 3 dimensions, which could be topological. So this was a discovery by Shinsei Ru and Andreas Ludwig and others who worked on this subject now already 15 years ago and classified all topological superconductors. So they found that conventional S-wave 3-dimensional superconductors, well, those are not topological, but you can cook up a version of them which actually become topological. And so you could ask whether there are similar singularities for those superconductors. And we found that, yes, there are, and they were on that list of, which I showed to you, of superconductors in different dimensionalities. But there is something which we could not fully prove, which is, you see, I'm solving these complicated equations for the gap function. They're complex, they have complex solutions. I've never really solved them. I just declared that they have some solutions. But what if, as I go to these complex solutions, my gap function develops a piece which is just like a conventional S-wave superconductor? See, so it's a topological superconductor with a very special gap function, not the conventional gap function. But once the equation is complex, who knows what happens? What prevents it from deforming itself as, I have some imaginary units floating around and becoming more like a gap function for a conventional S-wave superconductor? And then this will go away. Okay, and I don't know. For that, I think further analysis of the gap equation should be done. Is there any symmetry principle? Well, in general, it's like what enforces these special 3-dimensional superconductors to be topological? What exactly makes them topological? Well, they're constructed. There are examples of these superconductors, but the examples are actually constructed not in terms of interactive fermions, but in terms of a certain gap function imposed on you, right? So the examples involve some lattice, some fermions moving in the lattice, and you cook up some very complicated gap function with very complicated momentum dependence, and you say, oh, look, this is a topological superconductor. But in order for that to work here, or to understand the spectral form factors, I need to arrive at these superconductors from interacting fermions. And then I have to argue that whatever feature enforces them to be topological will remain, even if as my time, well, even as I'm trying to solve this weird, unusual gap equation. Okay, so I know it's a long answer, but it kind of tells you that, yes, there is definitely a room to understand what's going on here. Because, so for P wave of the kind I looked at, that feature P equal to 0 gap vanishing is robust, and you can't get rid of it by some situation. But other topological superconductors might be so convoluted that maybe, well, I don't know, maybe they can be perturbed away from whatever behavior your gap function had. And then the features I'm describing, these singularities would be absent. But so I cannot tell right now whether for these superconductors, these features will be present or absent. I need something more concrete to work with to see this. But again, the example I showed here, plus some of the other examples, well, in its classification table, they're definitely of this type, where the singularities are present and robust, despite being far from low, from the part of brilliant zone where low line excitations are.
Just a comment. Victor, if you can run this movie backwards a bit, I find the slide
But how far?
quite far to the middle,
Ah, middle. But
to some simple slides. When you
this
compute,
slide? Relatively
yeah, when you compute combinatorically.
Okay.
This slide.
this slide. That's the only time I have anything combinatorical.
Yeah, so as you can see, as soon as number of sides is finite, partition function is a polynomial of e to the t. Right? It's a polynomial, right? Finite number of
Yeah,
terms. Polynomial. Okay. So when n goes to infinity, it stops to be polynomial, but it remains what people call the entire function. Entire function is functions which have singularities at infinity, essential singularities at infinity, but not in the plane, because it's polynomial. But it may have zeros. Okay. So and you probably study the position of zeros. Can you summarize them?
So as soon as you have zeros,
But let me repeat. Entire function, polynomial, limit of entire function. It has singularity, essential singularity at infinity, which means Stokes lines and anti-Stokes pattern, and zeros in the middle.
but
Can
so
you
in
summarize that?
dynamic limit, those zeros can condense into other types of singularities.
Okay, but can you summarize the analytical structure of this entire function?
So I don't.
Let me ask you
Yeah.
another question. Do you know Lee-Young's theorem?
Yes, but that applies to complex magnetic fields and not to complex temperature.
It's the same parameter.
So there are some differences between
is,
complex temperature and complex magnetic fields. But even if we concentrate on complex magnetic field,
Just hold. So Lee-Young singularities, it depends on its polynomial, which depends on the argument E to the magnetic field divided by temperature. You can make the argument complex either by magnetic field or the temperature, it doesn't matter. And it's applied for much more complicated problem, which is E Heisenberg. So I wonder what's analog of Lee-Young theorem. This is probably what you do.
but so
In
then
this
we
case-
need to clarify what Lee-Young theorem is. So in Ising model, what actually happens is that in thermodynamic limit, if temperature is the transition temperature for the Ising model, then the Lee-Young zeros as a function of complex magnetic field, or better to say imaginary magnetic field, they condense on the real axis. So if you plot vertically magnetic field, complex imaginary magnetic field, horizontal temperature, there's the condensation of these zeros, which actually leads to a partition function being singular when temperature is equal to T. And something very similar happens here. Now, this particular
So what exactly happens here? If I draw a complex plane, so what are positions of zeros?
So here for this particular partition function, it's long, complicated enough to I didn't study it. But I showed you a very simple partition function very early on. Let's see how for this one. For this one, everything is known and was not obviously.
But I'm not asking about that one.
Yes.
I asked about the previous one.
The previous one I have not studied, so I cannot tell you where those zeros are. But I know exactly where the zeros are here and why they lead up to these discontinuities. And I believe that these discontinuities are very similar to this, because these are discontinuities in the derivative of log z squared. And in the function I just showed, there's exactly the same discontinuities in the derivative. So this is log z squared, and every of these points, each of these points, there's a discontinuity of derivative, one derivative, another, right? So it's the same type of discontinuity. It just looks different, but it has kinks in z squared. And so I don't know, I did not analyze zeros of this object. It's complex enough, so just to look at it is difficult enough. To look at it at some time is difficult enough. To analyze zeros, I would need to look at complex times. I would need to promote T to a
But this
complex
is
variable.
this is what expected
Yes.
you do. You
Well,
want to understand positions of zeros on complex plane.
Yeah, I mean-
temperature, whatever you call it.
Say so, but I was more interested to see whether there are singularities other than kinks. And those ones which I found, they are not kinks, they're logarithmic singularities, and they are due to more profound phenomenon. They reflect the structure of the gap function. But here I can tell you where the zeros are. I know. That's easy enough. I have an analytic expression. All the zeros here are on the unit circle, and they condense on the real axis and lead to these discontinuities on the derivative.
Like young.
Well, usually they're called Fisher zeros, and actually that other paper which I referred to, this one, it goes through this analysis. That's a statistical mechanics paper in Journal of Physics A from 1984. And they actually go at length. This is the paper which pointed out the difference between Lee-Young zeros and Fisher zeros, and in what ways they don't behave similarly. There are some distinctions between them.
Other questions? Let's thank Victor again.